Okay, I think we can begin. All right. It's a pleasure to come back to the workshop on fluids and PDE. I hope everybody had a restful weekend. And our first speaker for this week and for this morning is César Nietzsche. He's from the Universidade Federal do Rio de Janeiro, and he's going to talk about the role of small frequencies in the large time behavior of the damped wave equation. César, you have the floor.
Thank you very much, Elena. I would like to thank the organizer of this meeting, which is very, very important to me because in the earlier versions of this meeting, especially one in 2011, another one in 2010, I had just arrived to Brazil a few years before that, and participation in this meeting and in these previous versions was very important for me in terms of getting to know the Brazilian community working in PDEs and close to fluid mechanics. I got to know people that later became collaborators and friends. So I have a very special, it was very important in my early career in Brazil, the participating of this meeting in these previous issues. So I would like to thank once again the organizers of this one and the previous ones, especially Elena and Milton, who have been very generous all along my academic career here in Brazil. Thank you very much, all of you. Okay, so I would like to talk today about what small frequencies do in terms of the large time behavior of norms of solutions to the damped wave equation. So let's start. As every good talk, I will try to divide it in three parts. I will try to introduce the ideas and why this is interesting. And I will then talk about how the linear damped wave equation is the one that has certain nice properties which are related to the heat equation in terms of decay of solutions. And then I will try to show how these linear damped wave equation properties make a very important influence the behavior of the semi-linear damped wave equation with absorption. I will be more specific and careful about this later. So first of all, let's start with some very basic mathematical physics. If we have conservation of energy we have a temperature, U equals U of xt, and then we use conservation of energy for the heat flux Q, which we know by Fourier's law, which is proportional to minus the variation of temperature. We combine these two equations, and then we obtain the heat equation for temperature. Partial derivative in T of U equals to the Laplacian of U, and we have an initial condition, initial temperature, U sub 0 of X. Solution is given by the convolution of the Gaussian kernel with this initial velocity. And from the mathematical physics point of view, we have a problem here because as we are defining the solution, our solution is a convolution. We have that signals, information propagates with infinite velocity, which is not physical, right? So then we would like to somehow address this issue, this question. I have to say that I have talked to physicists, and many physicists don't give that much importance to this for many reasons, at least in terms of what Carlo Cattaneo tried to do in the late 50s and late 60s. Carlo Cattaneo was an Italian mathematical physicist that worked in many different areas, amongst them general relativity, and also the mathematical formulation of many solid mechanics problems, all right? So then, when trying to work in general relativity, he tried to somehow get rid of this problem of the infinite propagation of signals, or infinite velocity propagation of signals, and he proposed to introduce a delay in the heat flux. So in other words, the heat flux at the time t plus epsilon depends on the gradient of U at a past time t. And then he introduced this first order approximation that we see here in terms of Q for the heat flux. And then when you plug things in, you obtain what he called a hyperbolic heat equation. What is the hyperbolic heat equation? This is equation here, which resembles both the heat and the wave equation at the same time, because you have the second derivative with respect to T of U minus the Laplacian of U plus a partial derivative of U with respect to T equal to 0. He worked with this equation, he obtained some results, but the point is, for his goals of trying to modify the heat equation in order for it to be compatible with general relativity, he didn't succeed, because this equation, when he tried to work in the general relativity framework, produces some other physical paradoxes which make it not appropriate for solving the problem he posed. However, this equation has very important application. It has natural physical meaning in terms of mechanics of solids, which I'm not going to talk about, because I would like now to say that this equation, the equation that we have just saw, comes in naturally in physics in other situations. For example, when you have Maxwell's equations, but now Maxwell equation with this damping term, this term which it's here minus J, which is the current density. You see, if we didn't have this current density, if J would be 0, then there's just Maxwell equations in vacuum. And then we know that we can decouple those equations in terms of obtain two wave equations, one for the electric field, another for the magnetic field, right? So then if we try to do the same, play the same game right here, but now, remember, we have current density, which is proportional to the electric field. It's kind of Ohm's law. Then we obtain two uncoupled damped wave equations. The one for the magnetic field B, which is exactly the same as the one we had before. And this second one for the electric field has an extra term, which is a gradient of the divergence of E, but it's not very difficult to see, especially if you go to frequency space, that we can make an orthogonal change of variables, and then this equation reduces to this canonical form, like in the first one, except that for a factor over there in one of the three components of the electric field. So these equations appear naturally now in a more wave-like behavior. In the first one, we thought of it as, okay, let's fix, quote unquote, the heat equation, and we obtain this. Now we are just purely in a wave equation context, which is very similar to this other model, which is pretty common. It's textbook example of you have a Heaviside proposed in the late 19th century, this transmission line model to model the evolution in time of voltage and current in a long electric transmission line. Think of underwater transmission lines, cables that were joining Europe and the United States in order to carry telegraphic signals. And then playing pretty much the same game of taking derivatives and substituting in the other, you can decouple these equations for voltage and current and obtain these two, and again, telegrapher's equations. That's the name that Heaviside used. And you see they're the exact same thing as before. So you can call them either the hyperbolic heat equation or damped wave equation, depending on where you start from, depending on what's your favorite flavor. So you see these kind of equations appears very naturally in different contexts physics, and you have to take into account that you may be looking for different things. Is it a heat equation or is it a wave equation? The properties are more like one or the other. Of course, it's going to depend on what you're looking for, on what you're trying to understand. What I'm interested in is the following. I'm trying to see how this damped wave equation, which I'm stating here with initial conditions, behaves with respect to decay of these two quantities, which I call E of t and K of t, which are the natural wave and heat energies, right? If you just play the standard game, you multiply by U, or dt of u here and integrate by parts and whatnot, you see that these two quantities have negative derivatives, so they decay. So that you want to understand what's going on with them for long t, for large t, I'm sorry. And the main idea here, which is going to be the guiding point in our work, is that for small frequencies, right, solutions to the damped wave equation behave like the heat equation, right? And we already do know that small frequencies are the ones that determine completely the behavior of the heat equation or the L2 norm and Sobolev norms of heat equations, right? So then we're going to try to use that theory and use the decay character, which I will define, of course, later, and I will try to remind you of what it is and how it works and why it is important. And we use that to improve estimates obtained by Nakamura and Kawashima, Nakao, and Ono for these two energies, for the damped wave equations, through other methods, okay? That's the main goal. So the takeout is the following. For most frequencies, the damped wave equation behaves exactly pretty much like the heat equation, and that determines the long-time behavior of these norms, the natural heat and wave energies for solutions of this. And of course, after that, I will try to use these results for the linear part in order to understand the long-time behavior of solutions to this semi-linear damped wave equation with absorption. So now we have a non-trivial right-hand side minus absolute value of u to the power alpha times u with alpha greater than 0. And then we will make use, there is already a lots of theory about these kind of equations. And we will use the results that we know now, or that we will know later, for the characterization of decay for its linear part to improve known results in different function spaces, in L2 and in some other spaces in weighted L2. I will be very specific about that later for this equation. So let me make a couple of comments here. If you forget the wave part here, I'm putting this little hand over this term, so you think of it as it being erased. So you have a heat equation with an absorption term, and it is well known that there is long time existence and the asymptotic behavior is known, but also it is known that if you have a plus here instead of the minus, then for the heat equation, there is this Fujita critical exponent theory, which says that there is a critical exponent alpha for this term with a plus sign, I insist, which divides the behavior of equations. So for exponents larger than that critical exponent, there is long-time behavior, long-time existence, I'm sorry, for small initial data, and for exponent alpha less or equal than that critical exponent, there are initial data for which solutions to that to the heat equation, nonlinear heat equation, blows up in finite time. All right. So the same thing, the analogous theory exists for this semi-linear damped wave equation. Only that just for sake of clarity in our paper, we decided to deal with this case first, in order not to clutter too much notation and too much information, because we wanted to emphasize how to realize or how to use this fact that for small frequencies, this whole equation, both the linear part, both the linear equation and this one behave as the heat equation would do. All right. So then we extended results for decay for this equation of results by Kawashima, Nakao, and Ono, Nishihara, and Zhao, in Ikeda, Inui, in Wakazuchi. All right, so now let's talk about the linear part, and let's try to make it clear what do I mean by behavior of the damped wave equation is analogous or it's the same as the heat equation. All the results that I'm going to quote right now will appear in 2022 in this joint article with my PhD student Armando Cárdenas. It's already available as a preview first or in the journal. It's already available. It's already online. All right, so we want to clearly explain what does it mean for the damp wave equation to have decay like the heat equation, right? And because we're interested in studying these two energies. So let's go first to see what the explicit solution to the damp wave equation is. Well, the explicit solution is given by the convolution with initial data, as usual in the wave equation. But now the fundamental solutions, K1 and K2 in frequency space, have this form. All right. So they are this product of exponentials and hyperbolic and normal trigonometric functions. All right. So in principle, this does not shed too much light into the question, the answer to our question. Okay. First of all, I already said that there was work by Matsumura in 1976 concerning decay of these solutions, and this work by Matsumura says that the evolution by these two R1 and R2, which are the fundamental solutions in physical space, of initial data in L2 intersection Lm with m between 1 and 2, the decay of the L2 norms is given by these expressions, all right, which happen to be exactly the same decays that you obtain for the heat equation, right, with the same initial data. So if instead of R1 or R2 here, you have the Gauss's kernel, then the decay would be exactly the same, right? In particular, note that first, if m equal to 2, or in other words, if our initial data is just in L2, the best thing that we get here, because m equals 2, is just boundedness. You have no decay rate, okay? And notice that when this right-hand side gives a decay rate, it's because you have to have your initial data more concentrated than L2. In other words, your initial data has to be in L2 intersection Lm. So you need extra information. All right. Now, let me just give you in a couple of lines, why is it that decay looks like the heat equation? I took K1, one of the, in frequency space, one of the two parts of the fundamental solution. The same argument, the same thing happens for the other term, for the K2. So for small frequencies, for modulus of psi less or equal than 1/2, this is the explicit expression for my K1. For in that range of values of psi, we have this inequality relating. You see here we have square root of 1 minus 4 modulus of psi squared minus 1. And this is bounded from above and below, but by things proportional to minus modulus of psi squared. And this is exactly this square root is the one that we have here as an argument of the hyperbolic cosine. And the hyperbolic cosine is just a sum of the exponentials, right? So then a simple trick, a simple argument shows us this hyperbolic cosine part is bounded from above, but this exponential with now this argument right here, and this square root of 1 minus 4 times modulus psi squared divided by 2 is exactly one of the parts, one of the components in this
Yeah, we'll wait a little bit. See if César comes back up. Yeah, César left. He might be trying to enter again. So I think César's internet probably went down. So I'm trying to talk to César to see if he can come back up, maybe reroute his internet through his 4G network. Try to deal with this. Okay, so I tried to talk to César by phone, and I think maybe even his 4G network is down or something. He's not answering even the phone. So, Ernie, what would you like us to do? Would you like us to go to Gather Town early? Oh, this is a pity.
Well, maybe we can wait a little bit more.
Okay.
Maybe 5 minutes. The problem is we cannot pause the streaming. So actually, my message there, Deisha, it was meant to somebody else because Juliana was asking if she should pause or stop the streaming. And otherwise, we'll have two videos. And then, okay, maybe later I can put them together.
Oh,
well,
I'm sorry. César told me that has a blackout at home.
Yes, exactly.
Okay.
Oh, there you are. Okay, great.
It was a blackout, and also the cell phone signal had a blackout. That happens roughly every day, every other day, but it hadn't happened last week. So everything goes out, both electric light and cell phone signal. So
and the phone signal. Okay, yeah, because I tried to talk to you and I called you, but okay.
No.
All right.
Back to.
Okay, so you want to resume?
Yes. I'm sorry about that.
Okay, no problem.
Okay, so hold on a second, please.
Yeah. No, we were not seeing our screen, César.
Yes, I know. I'm.
Okay.
I had to do things. Do not commute when you try to do it this way. All right. Yes, I know. All right, now we're good, right?
Yes. Well, yeah. Okay. You
Yes,
can't make this full screen, can you?
I hope so. But when I go full screen, now it's black, right?
Yeah. Maybe if you just click on this little arrow that you have right on your right hand side in the middle. Yeah, a little bit more to the right.
That's good.
Okay. All right. Fine. All right. Let's go for this. Okay.
Okay, now I'll put things in a smaller window so that at least something works. Sorry about that. All right, is it okay if I resume from here? Okay, second. All right, so
Yes,
I was trying to argue just why is that the solutions of the damped wave equation behave like solutions of the heat equation. And the key point here is that the fundamental solution to the damped wave equation, here I said that I was going to analyze just one of the two terms, K1, in frequency space, because the analysis for the other term, K2, is analogous. What happens is that this hyperbolic cosine for small frequencies, frequencies which are less or equal than 1/2, the hyperbolic cosine, which is just the sum of two exponentials, we write down that estimate from above. So now this exponent here, square root of 1 minus 4 times modulus of psi squared divided by 2 times t, we use this inequality. Now remember that I said that this term here is bounded from above and below by something which is proportional to minus norm of modulus of psi c squared. And then using that inequality, I get this exactly here, that the hyperbolic cosine is bounded from above by e to the t divided by 2 minus times exponential t to the minus t times psi squared. And there we use that this inequality right here, and then we're good, right? So that's the key point. For small frequencies, K1 and K2, both of the terms in our fundamental solutions, are bounded from above by the Gaussian kernel in frequency space, right? By this Gaussian exponent, the Gaussian function right here, right? So then that's the key point for understanding what happens when we're using the heat equation, because this is in frequency space, the solution that we obtain from the heat equation. So now, to summarize the estimates, what we're going to do both for K1 and K2 is the following. We are going to divide K1 and K2 in high, middle, and low frequencies. For high frequencies, we have just sines and cosines. So the only thing that in the fundamental solution, which are bounded, so the only thing that matters is the e to the minus t part. With an analogous argument, we do the same for K2. For middle frequencies, one of the two parts of the fundamental solutions, the K2, we have to do some computations, but we end up showing that this K2 is bounded from above by an exponential in time. Notice that here the frequency variable psi just vanished. It didn't vanish, it just disappeared. For small frequencies, so we have the estimate that I showed you in the previous slide. So for small frequencies, really, we have to study the heat equation because that's the one that bounds from above in frequency space, K1 and K2. Right. So why is that important? Why are the small frequencies of the heat equation or the damped wave equation important here in this case? Well, because we use the Fourier splitting method. So let me show you just in 2 lines what the Fourier splitting method introduced by Maria Elena Schombeck does. You take the heat equation, we want to understand what happens to the L2 norm of its solutions. We play the usual game, you multiply by U, we take Fourier transform, and then after some very natural computations, which I didn't want to repeat because most of you already know how the method works, we end up working in the end with the following. B of t is a ball centered at the origin in frequency space with radius which is proportional to t to the minus 1/2. And we obtain this inequality that we see here. Let's take the left-hand side is just the product of t plus 1 to the n times the L2 norm, which is the quantity that we want to bound from above. And there is this derivative in t right here. On the right-hand side, we have a factor of the form t plus 1 to the n minus 1. And we have this integral here, which is the one that we want to bound from above, right? Because then when we integrate in t and then we divide by t plus 1 to the n, this factor on the right-hand side, t plus 1 to the n minus 1 will vanish. There are some cases where you have to do some tricks, but this is the main idea behind. All that matters is the following, is the expression for the solution to the wave equation, exponential to the minus 2t modulus of psi square times modulus of the Fourier transform of the initial data square.
Oops.
Integrated on the ball B of t.
Okay.
No, I'm back. And you see, when t is large, the ball is very small, and this exponential becomes pretty much 1. So what matters really is the initial data, right, for very small frequencies psi. That's the guy that will give you decay rate, because the behavior of that guy will influence on how this integral on B of t behaves, right? So then that's really the important point here, understanding, at least for the heat equation, what does the Fourier transform of the initial data looks like very, very close to 0. For this, we have to understand what the decay character is. So the decay character, roughly speaking, looks at the initial datum, U of 0 hat, and sees whether it looks like norm of psi to the q for some q, right? And with that information, notice, I'm looking at the initial datum data near the origin, which is exactly what I was saying in the previous slide, right? So then, once I get that information, I can understand the long-time behavior of solutions, not only to the heat equation, but to many other operators which are diagonalizable. I will say what that is later very carefully. And you see, roughly speaking, if I were just doing Fourier series, what do I do? Well, I write the solution to the heat equation through separation of variables explicitly, and I see that when I compute the norm of U of t L2 squared, the first term in that series has an exponential term. It's exponential to the minus the first eigenvalue of the Dirichlet Laplacian, and that guy gives me the slowest term in that series. That will be the decay rate. So in some sense, for understanding the decay rate of things here in Rn, this decay character plays the same role as the smallest eigenvalue of the Laplacian, right? So then that's the key point behind things. The decay character was introduced by Clayton Bjorland and Maria Elena Schombeck, and then Maria Elena and myself extended some work, and Lorenzo Brandolesi gave a very nice wrap up of our previous work. I will be more specific about that work a bit Very simple. All right. So now this is the technical part. Because I got just slightly sidetracked with this because of this blackout thing. I will say this is a technical definition. This piece of Q of U0 picks the Q for which the initial datum looks like normal side to the Q, if there is one, right? That's what I'm saying. And then I define the decay character as that guy at the Q, which makes the previous quantity different from 0 or greater than 0 and less than infinity, if that number exists. So roughly speaking, this is a little bit technical definition. Just keep the idea. The decay character tells you whether for which Q the initial datum looks like normal side to the Q near the origin. The decay character can be explicitly computed, so we can check explicitly that our definition produces the same results that are unknown for decay for initial data of this form, for initial data in L2 intersection LP with P between 1 and 2, and for other initial data that we didn't know how to compute it in previous forms. The thing is that Lorenzo Brandolesi gave a finer understanding of the decay character, because as you might see, I'm saying the decay character is such number. If this number exists, we suppose that our initial datum was kind of monotonous around the origin in terms of frequency space, so that our limits here were well defined. Well, but then Lorenzo noticed that this does not have to be the case. He found examples for which in our definition, the decay character does not work. In our definition, the decay character does not exist, by constructing initial datum which are very highly oscillating near the origin. But then he produced analogous definition that coincides with us in the cases, for example, in the previous cases that I showed you. But more important, he characterized the existence of the decay character in our definition in terms of the decay character belonging to a certain subset of an appropriate homogeneous base of space. The point is that for operators, for differential operators that are like the fractional Laplacian or this Lamé-like looking operator, which are diagonalizable in the sense that when you go to frequency space, the matrix of symbols is diagonalizable, right? And the diagonal matrix looks like this right here, is just minus some constant normal side to alpha. Then the Fourier splitting method works, and then the decay character leads us to the following result. So diagonalizable operator, think of Laplacian, vector Laplacian, or Lamé-like operators, right? You will have the decay character for initial datum, and then solutions to that linear equation are bounded from above and below by expressions in time with the same exponent, and the exponent contains that decay character R star. So in other words, we have a machine that we take the initial datum V sub 0, we read its decay character, which can be computed. It's not some like kind of, there exists some decay character. You can compute in many important instances. And then that decay character tells you how does the norm behaves in terms of decay from above and below. All right? That's a nice characterization result, which can be refined through this work by Lorenzo, in which, okay, now the algebraic decay of a solution to the heat equation or to any of these diagonalizable operators can be characterized as being bounded from above and below by the same exponent with the decay character, if and only if the initial datum belongs to this subset of this base of space. All right, so now we have a rather complete theory for characterization of algebraic decay of solutions to linear operators, which are pretty much like the vector Laplacian. And now we have to go back to our problem, because now Remember, these are the estimates that Matsumura proved for the damp wave equation, which are exactly the same as the heat equation. So then we can prove using that idea of dividing our study in high, middle, and low frequencies. High frequencies and middle frequencies, no big deal. They provide exponential in time decay for the L2 norm. Small frequencies behave like the heat equation. So then we can show now that for each of these Ri, or in other words, for each of these components of the fundamental solution to the damp wave equation, we have a decay which is exactly the same as the heat equation, which is minus n divided by 2 plus the decay character of the initial datum h, right? But now we are in damp wave equation context. So we have initial position, quote unquote, initial velocity. So we have initial data f and g, right? So we have two decay characters. So the decay of the L2 norm behaves like, well, minus n divided by 2 plus the minimum of these two guys here, of the decay characters of each of these f and g. And as a result, the other energy, the wave energy, has a similar behavior. Why is this interesting? Why is this important? First, we can treat all these estimates in a unified way. We don't have to split things in, oh, if the initial data looks like this or like that. We have a machine, the decay character will read the initial datum. And once we know the decay character, we work with all at the same time. We know what happens. Our estimates include those already obtained. There are natural extensions because you see, I was talking just about the L2 norm and the wave norm. If we have higher Sobolev norms, we can just very naturally extend these results with much less work than in the than Matsumura, Kawashima, Nakao, and Ono, and Ikehata did because of the properties of the decay character. And moreover, notice that here we have that F and G may have different decay characters, so we can specifically say which of these two guys, either F or G, is the one that gives the decay behavior. One of them is going to be larger, so the other one, the one that is mean between the two, is the one that really matters in terms of decay. The other one will produce a faster decay that after some time t, we are not going to see it compared to the other guy. So we can specifically play games and choose different F and Gs to produce behaviors that we want to see. Okay, right. Now, enough for the linear part. Let's go for the non-linear part, for the semi-linear damp wave equation with absorption, right? Kawashima, Nakao, and Ono prove results for this equation, which I insist now the right-hand side here has the good sign to make things easier in terms of existent results, right, and decay too. And I insist, as I said before, if we have a plus sign here, our results would be valid for certain ranges of alpha, which we didn't include in our paper. But remember, if there is a plus sign here, we will encounter the same Fujita critical exponent phenomena as in the nonlinear heat equation in terms of blow up of solutions of positive within positive initial data for some exponents less than the critical exponent, which depends on the dimension, right? And so we didn't want to include that in our paper. It would be kind of a very natural consequence of our result, but it would have clogged our paper a bit too much. And now, of course, our heat energy, quote unquote, the L2 norm stays the same, but now this extra right-hand side term makes that our wave energy contains an extra term of the form L to the alpha plus 2 norm of U of T. Kawashima, Nakao, and Ono prove results for the standard case in which the initial datum has to be more concentrated, so has to be in these LM spaces on top of H1 times L2. But we can naturally, and here I'm just stating the result, the values of alpha for which these estimates hold depend on the dimension n. And let's notice first, in this case here, in the first part of the statement of Kawashima, Nakao, and Ono's result, the best thing you get, because your initial datum is in H1 times L2, is that the heat energy is bounded from above, and that the wave energy has this decay. When they introduce some extra conditions on initial datum, then their range of values of alpha become smaller, become different, and they obtain some decay for both heat and wave energy. The thing is that now in our results using our decay character technology, our ranges of alpha are larger than what they obtain, and we can express explicitly the decay rates in terms of the decay characters for any initial datum, which is in H1 and L2, provided, of course, that the decay character exists. Remember that there is this characterization by Brandolese, which says in which circumstances the decay character, as we define, exists. So for those guys, we have these expressions, which again have many the features which are very interesting. First of all, we recovered the results from Kawashima, Nakao, and Ono, right? And we have a larger range of values of alpha for which the estimates hold, right? So our results, our estimates are somehow finer and allow us to use somehow their techniques for proving the estimates, but we can go farther in the range of values of alpha in the exponents of the nonlinear term minus modulus of u to the alpha times u, right? So in some sense, we go a little bit deeper into the structure of these particular equations. In the results by Kawashima, Nakao, and Ono, they had to choose F and G in the same L2 intersection LP, right? But notice that now we separate this mu of Fg is the minimum of these two guys. So now we are able to say which one of these two guys is the one that really produces the decay. So we are able to somehow separate the contributions, the importance of both the U sub 0 and dt of U sub 0 on the decay rates. Right, so somehow we are able to go to have an understanding in a finer way how do initial data influences the long-time behavior and decay, right? And moreover, now we can obtain finer estimates in the following circumstances. If now our initial data is weighted in L2 by this exponential here, Nishihara and Zhao proved some results on decay of solutions, which were quite complicated. As this space, this L2 weighted space, is in L1 gamma, and we can use, and we know how to compute the decay character for L1 gamma, we immediately obtain these decays for our heat and wave equations, which are finer than what they obtain and are clearer because we just say, look, this is a subset of L1 gamma, and L1 gamma has a nice decay character which can be explicitly computed, and we have already all the machinery. So improve the results both in terms of decay rate and of clarity of why is that that solution decay. You may say, well, look, this is a weighted L2 and weighted by an exponential. This should be clear that it has a faster decay. Yeah, it does. The linear part decays so fast that the nonlinear part, this minus n divided by 4 here, is the decay given by the nonlinear part of our solution, which we remember we're talking about. Let me save that comment for a little bit later. Also, Ikeda Inui and Wakasugi, they used now an L2 weighted space, but now with these polynomial weights, okay? And then they also proved certain results that are somehow technically complicated to obtain. Again, as this space, this weighted L2 space, is a subset of L1 gamma, we are able to prove that the nonlinear part is the one that drives the decay, because the linear part decays quite fast, and we're able to do this in a very efficient way, a very quick way, and we obtain an improvement on the results. And once again, our ranges of alphas of the exponents of the nonlinear part are slightly larger than theirs. How you proceed? Very naturally. We have mild solutions only because we are working with this damped wave equation, and then we divide the study in the linear part, which we already did it, everything from before, and then we have the nonlinear terms. And in nonlinear term, we do the same, we play the same game, small, middle, and high frequencies. For high frequencies, there are some technical issues that we have to deal with. They're not completely trivial. Gagliardo-Nirenberg Sobolev embedding use. There are some ad hoc tricks that you have to use. But anyway, for high and for middle frequencies, once that you deal with these difficulties, everything has an exponential decay in time, right? Exponential decay in time of the norm. So then we're good. And then for small frequencies, we already have played our game. We do know that for the linear part, for the linear part, we had the estimate for the heat equation. We work with an analogous way for the small frequencies of the nonlinear term, using again the estimates for this heat equation. And then we put everything together, and we have to find some adapted version of Gronwell, find Gronwell to be more specific, to put everything together. So in the end, I think that the take-home thing here is the small frequencies are the ones that drive the decay here, and as they behave like the small frequencies of the solutions to the heat equation, then everything is fine. And this phenomenon is not just reduced to this particular damped wave equation. Let me go back just to give you, forget the nonlinear term for a second. If we had here on the left-hand side in this third term, dt instead of dt of u, dt of Laplacian of u, which corresponds to what is called the strongly damped wave equation, we can play the same game. We can go through the same road. But now very interesting things start to happen. What I'm describing now is current work that we're doing with Armando. We're pretty much finishing the write-up of the paper. For that strongly damped wave equation, in which instead of having dt of u, you have dt of Laplacian of u, if you play the same games, you will notice that the L2 norm has very interesting behavior. There are, depending on the dimension, there is a critical decay character, which does the following. For initial data with decay character below that guy, the L2 norm of the solution grows algebraically. For this exact value of the decay character, the norms of the solution grows in a logarithmic way in time. And for decay characters larger than that value, all right, over there, the L2 norm decays. So which is a very different behavior from what we're used to. This comes from the fact that with this new term, the fundamental solution, the term that really matters in the fundamental solution, has a singularity in frequency space at the origin that is not killed by the other parts of the fundamental solution, because it looks different. Instead of having an hyperbolic trigonometric for low frequencies, we just have a trigonometric, and you have no way of getting rid of that singularity. So that's a very interesting point. Of course, if we go to the wave energy for that new strongly damped equation, then things start to look more in a more reasonable way. But then you see that the method provides some certain subtleties of the decay character, tells you in a very specific way how the universe of your initial data can be separated in terms of properties. Here, for our standard damped wave equation, you will obtain the decay as we see here. And you see, again, I'm just singing the same song again. You can specifically separate the contribution of the initial datum F, the initial position, and the initial velocity G, and you are able to say, well, this n divided by 4 comes from the contribution of the nonlinear part. This added first term comes from the contribution of the linear part. So you can say who is the one that has the slowest behavior, either the nonlinear part or the linear part. So you obtain finer information with respect to other estimates, because we're considering all the possible initial data at the same time. And we're just have this kind of a machine that reads its decay character, and you just can separate the behavior in terms of that one. And for other systems, like the one with the strongly damped wave equation, as I said before, the one in which you have dt of the Laplacian of u, you have these other interesting phenomena which we can detect using the decay character very quickly. So thank you very much. That's what the message I tried to convey to you. Thanks a lot.
Let's try to have like one question at most, because we're very late. So does anybody have any questions? You can unmute your microphone and ask, or you can use the chat if you wish. Okay, so if there are no questions, then let's go ahead and thank César, and let's reconvene to the